So, hello, I'm Aasma. I'm a lead database consultant at Cybertec. I've been doing this, helping others run Postgres stuff for 13 years now at Cybertec. But enough about me. This talk is probably going to be long and heavy, so I'm just going to jump right into it and talk about explain. So, everybody loves explain, right? How many of you are aware of what explain is and does? So, about half of you. So for the rest of you, I'm going to do a quick overview of what explain is. So explain tells us how the database intends to execute our query. So when we give it a query, it figures out what's the correct algorithm for it. And if we run explain analyze, then we can see that did the plan actually work out? Was that a good idea to do, or maybe it was a bad idea? And if we want to do have some extra information, there are tons of options that we can add to explain. We can tell it to add some verbosity, tell us what the settings were, how many buffers were used, write ahead log statistics, and so on and so forth. And maybe it's time to add an explain everything command in case we want to get all of the information at the same time. But I'm not going to go into detail about this stuff. We are going to talk about all of the stuff that explain does not do. But the first step would be to understand what it does. So I'm going to have to start with a warning. There is going to be code here. So in case you're easily scared by code, be warned. And there's going to be a lot of it. And I mean really a lot. So if you cannot read this text, I advise you to move slightly forward and find a place in the front here. But if you want to follow along on your computer, the stuff will be available on the conference website when I get the chance to upload the slides. But you can get it right now from the pgconf.de website. It was presented there last year, and the slides are available from the schedule. So let's start with a crash course on how to read explain plans so we are all on the same page. So the explain, what it does, it represents the Volcano execution model tree that Postgres builds internally to execute the plan. It's called the Volcano model because it's wide at the bottom, narrow at the top, and the rows come out from the top. So just to show you what it looks like, here we have a simple query. We are just joining a couple of tables, have a where clause and the limit there, and tell Postgres to explain it to us. And it comes out with this type of structure, and you read it by going from the top down. So when we start to read the data from this query, we first ask the topmost node, which is the limit node, give me a row. That in turn will ask the next one, the nested loop, give me a row. And that one will then run both of its subqueries in parallel. So for each row from the first one, it will execute the second one. And it will ask for a row from the sequential scan. And for that row, it will run this index scan. And the important part here is the costs. You are mostly should be looking at the second number there. That is the planner's idea of how much is this node going to cost to run. The unit of the cost is not important. It's some arbitrary unit. Hopefully it's correlated with the time that the node will take. But because this is based on statistics, we all know what they say about statistics. So it might be completely wrong also. And the value is inclusive, and we can see that usually it's bigger than the one before it, and the exception is the limit here, which is not going to read everything below it. And we also have the number of rows that we are planning to get out of it. So that was the plan on how to execute this query. Let's now run it with explain analyze. This will get us a bunch of extra information. But because we were already looking at the cost information on the previous slide, so let's turn that costing off, and now we can fit this actually on the screen. So when the cost was there, the units in the parentheses were unitless. It's just some arbitrary number that is just compared against any other plan that we might have. But when we are running explain analyze, the units in here are milliseconds. So this whole query took us 0.3 milliseconds to run, and then we can go from the top and see, okay, 0.28 milliseconds was inside the limit, and the nested loop was also 0.27, and then we have the sequential scan was taking only 0.16. So that's how we can figure out where the time went. And we can also see some interesting extra stuff, like how many rows were removed by the filter, and how many rows did we actually get out of it, and how many times each node was executed here. And the final part that we will need to understand here to follow along is the buffers command. And because databases are dealing with storage, how many pages of data we had to look at is actually a really important part of the performance story. And if we enable the buffers option to explain, we will get back the information about how many pages of information were found in the system cache. So that would be the hit number. And the other one is read, which is how many were read from the operating system. Now, this does not immediately mean that it came from disk. And for that, to understand if it actually came from disk or not, or how much time did it take, it helps to turn on track I/O timing, which will give us this I/O timings line here, which is telling us that actually reading those 2,000 pages, that's 8 kilobyte pages in Postgres by default. That's 16 megabytes. Reading those 16 megabytes was only 2.7 milliseconds. Probably this stuff came from the page cache, from the operating system. Okay, but that should explain the explain plans reasonably well enough, so we should be able to follow along now. So let's start from toast. As a first step, I now need a demonstration schema, so the queries are somewhat interesting to look at. The schema here is going to be about some reports that we are collecting metrics about. So we have a reports table that has an ID. It has some rule set ID reference, and there is a bunch of data stored in a JSON-B column that would be like a metric and a value. And then the other interesting table for us will be a rules table. There is again a primary key, a rule set ID, and then a number of the rule, which metric field is it talking about, and then the maximum value for that field. So simple enough schema. And we probably also want to have indexes on the rule set ID so we can reference those two tables together. And now we need some data to go along with it. So I'm going to just generate into those tables 10,000 reports. Each one has 1,000 metrics. So quite a large field. And then in the rule sets area, we will have 100 rule sets. Each one has 10 rules. So once this is done, we will get some tables, and mostly we are worried about the reports table. And we can see that the total table size is 159 megabytes, but the total data size is somehow larger than this. We will see about that in a bit. And the average size of this data column is 32 kilobytes. Okay, let's try reading all of this data back. We will run a simple select star from reports, read all of the columns, and nice, we get it back in less than a millisecond. That's pretty fast, right? So it could be a bit too fast, actually. So if we calculate the numbers, it's more than 300 gigabytes per second. And our system is probably not that fast. So maybe we should check what's going on. So let's try a different way. Let's use p-SQL's timing command, run a copy command to copy this same query just to device null to see if that has the same performance. And now we can see it takes actually 1.7 seconds. So that is a more reasonable number for reading 100 megabytes or 300 megabytes as it was. So why are those two numbers so different? To get into it, we first have to understand how Postgres handles large values. So as I said, we are using 8 kilobyte pages, and the values we are trying to store are 32 kilobytes. So to handle such large values, Postgres actually chops those up into 2 kilobyte pieces and inserts them into a secondary table that's called a toast table. And inside the main table in the row, we instead of the value, we just store basically a foreign key into that toast table that says this value is stored over there. And we can also just compress the data when it goes to the toast table, so we don't have to read as much back. And now when we are querying this data, when we read the row, we get the ID back, and we don't immediately go and fetch the data from the toast table. The fetching from the toast table will happen as needed when somebody is using the value. So in this case, when we run this explain analyze, this was throwing the results away, and we just read the pointer value from the main table and then decided we don't need this anymore and threw it away and never looked at the toast table. So detoasting was not triggered in this case, and that's why it was this fast. And this is actually fixed in Postgres 17, so we can run this explain in a way that we can get this information back. So we have to add this serialize keyword to our explain command. And once we do this, the query will start taking a much longer time, 1.1 seconds in this case. And it shows us that executing this sequential scan on this reports table was fast, but the serialization took 1.1 seconds. It still doesn't tell us that it was toast that was involved in it here, but at least we see that it's taking a long time. And what's still missing here is you might have some time to send all of this data over the network. So whether you care about that or not is a separate question. But at least if you use this serialize, the actual result will be much closer to the real query that is being run. But now let's look at some more interesting cases how detoasting can pop up in some slightly more complex queries. So here's a query to just join our reports with our rules using this rule set ID. And then we check from the data, does the metric field value exceed the maximum value for all of the cases where we have the rule number 1. Okay, so here we have the explain plan for this query. This explain plan decided to use a merge join that takes altogether about 300 milliseconds. But if we go into the details, we can see that the index scans that are below this merge join, they are taking 0.3 of a millisecond and the other one 3 milliseconds. So where is the other 99% of the time going? And another hint what's going on over here is this buffers value here. We can see that the index scans they are reading some data from the page cache, some from disk. But then this merge join itself, which should be joining together information that is coming from two sources. It should not be reading data. It's actually accessing a lot more pages in cache, and it's also reading from disk. So why is merging expensive and taking a bunch of time? The answer is this join condition that we have here. So this join condition actually needs the value of this data field to do the comparison. And this will execute the detoasting, will fetch the data from the toast table, and this is actually doing an index scan, reading the data and all that. So that's why it's accessing a whole lot more pages here. But it's really hard to notice that this is the reason why we are spending a lot of time here. We don't have any extra details in the explain plan about this detoasting. But it gets worse. So here's the same query, basically, but we eliminated this rule number 1 condition. So we are executing the same stuff for all of the rules. So now this query takes 2.5 seconds. And if you look at the amount of buffers we had to look at, it's more than 3 gigabytes of buffers that we are reading. And if you remind yourself, we had 300 megabytes of data. So why are we reading the stuff 10 times over? It's basically because dtoast does not remember the value that it produced. So when we are executing this condition here, for every rule, we again go to the toast table, reassemble the JSON document, execute this rule, and then throw the result away, take the next rule, and repeat. And that's why this is reading so much data. But how to find this stuff in your real execution plans that are not these toy examples that I have here? It's kind of hard, but some of the hints that you can look at today is that if you have an unreasonably high number of buffer accesses in an unexpected spot, that hints at that there is detoasting going on. And the other thing that you can do is just use your knowledge about the data and see if you have some large fields in your schema. Where are those fields used in your query? And if you use a verbose option to the explain plan, you can see how does it propagate through the plan and where might it be evaluated. So another example is here where we are running a query that is just fetching from the reports table 100 random data, 100 random rows, and calculating the length of the data there. So we convert this data to a text format, which is just formatting it as JSON and then selecting the length of it. And this is taking now 1.3 seconds. And we needed 4 megabytes of memory to sort all of those rows. And the number of pages that we are accessing is about 40,000 here, and we are selecting all of the 10,000 rows. And what's going on over here is that we have this data conversion to text format here. And this is triggering this detoast. But we don't actually need to detoast it this early because we can just pick the 100 rows and select the toast values for those. So we are doing detoasting too early in this case. So how to fix those types of problems? So this latest case where we are detoasting too early, we can use subqueries with an offset or a limit clause in them to set a boundary within our query to limit where are the evaluations pushed down to. So if we rewrite the query slightly, we have this, most of the query here is the same. The only difference is that we are just selecting the data field from the reports table And we have this limit here that acts as a boundary. And only when we have those 100 rows, we actually execute this length calculation. And once we do this, this runs almost 100 times faster. We only need 40 kilobytes of memory to sort all of this stuff. And we are using 100 times less pages from the system. And the reason is that we are selecting only this reports.data field from here. So we are sorting this using only the pointer information. And once we have done the sorting, limiting, only then we evaluate it to text format, go and fetch it from Toast. And we only need to do this for those 100 rows, not all of the 10,000. So you might want in some more realistic cases to do the T-toasting after you join or aggregate or do whatever things that reduce the number of rows that you have to find the data for. And the other case, when we were T-toasting stuff too late and T-toasting multiple times, the fix right now is to force the early T-toasting by doing a dummy operation. So if you remember the query here, we had this condition here that was evaluating the join clause, and this was reading the data field multiple times. And we do a slight transformation, so we replace the reports table here with the subquery. And the subquery doesn't do much, it just selects all of the data from the reports table, adds an offset 0 as an optimization boundary. It does nothing other useful things from the data, so logically it's a no operation, but for Postgres planner, that's a fence that it doesn't dare to cross. And then inside this fence, we add an operation that, again, does nothing useful, but it forces the executor to actually go and fetch the data field and convert it into in-memory format. And if we add this dummy operation, then the previous query that took 2.5 seconds now becomes 300 milliseconds, and we have a lot less buffers being accessed. And we can actually see that all of the access is happening here in the sequential scan when we are reading the data. We are not fetching the toast values within the join. So to recap, you have to be conscious where are you using large values in your plans. So the planner is as stupid as can be about Toast. It basically doesn't know anything that toasting exists. It's actually even worse. It considers that the toasted values are cheap to read because it calculates the average width based on the pointer, not on the actual data. You also need to think if you have to be eager or lazy. Do I use the values multiple times? Can I skip evaluating it and figure out where to do this? And then use the tricks I thought here to force the planner's hand to not do what you want. Just make it not do the stupid stuff. Okay, but moving on from Toast now. This topic is going to be about visibility. So we need a new schema. For this schema here, we are going to build a small task queue application. We are going to have some tasks that are in to-do, done, or failed status. There is a primary key. There is a foreign key to a job. That is one of 10 jobs. There is a status in what is the status of this task, when was it added, and when was it done. And then we add an index, so we want to find the oldest task that is to do based on this added column. And this index will let us do this because there is a where predicate that only makes it have those relevant rows. Let's add some tasks to it. So we just generate 100 to-do tasks for us. And now we are also going to need the workload, because visibility is something that is quite transient. So we need something to be running actively. And our workload is going to be consisting of two simple tasks. One of them is going to add a new task, and the other one is going to select the task that is still to do based on this added column, and it's going to be skipping everything that is being done by somebody else. It only selects one of the tasks and updates its status to done. And now to run this workload, we can use pgbench. It has some nice options to running custom scripts. We have those two SQL files. We're going to tell it to run 2,000 transactions per second using 8 connections for 10 minutes, giving us progress every 10 seconds. And that's going to look something like this, that we are nicely executing 2,000 transactions per second. The machine can keep up. And while this is happening, in some other place, there is somebody that is opening a transaction using a program that is notorious for leaving transactions open, executes a count star query, and then goes and gets a coffee to think about the result here. And this leaves the transaction open in this session. And so what's going to happen to our benchmark that is running? So the workload is going to pretty quickly tank. So we are running at the beginning 2,000 transactions per second, and it's going to be going down to 750 in a couple of minutes. And we're going to see lots of CPU usage, later I/O usage, and everything goes slow and everything is terrible. And this is when we get the call that our system is on fire, what's going on? And somebody goes and checks pgstat statements, sees that, okay, we have this task completion query, and this is now 100 times slower. Okay, let's get an explain plan, see what's going wrong. So let's see, how does the explain plan show us this problem here? So we have the explain plan here. We are updating our tasks, and to update, we need to get the one query that we are looking for. So this is doing an index scan in the tasks table. We are selecting 10 rows, and it takes 25 milliseconds to find those 10 rows. And even more curious, we are looking at about, 800 megabytes of data to find 10 rows. So what has happened here is that the auto vacuum is no longer able to usefully clean up the completed tasks. So they pile up in the index. Even though the task was completed, we still have that previous transaction open, and that might come back and read this data. So we need to keep it around. And there's also going to be in the index references to each one of those rows that is being kept around. And to make matters worse, because of the open transaction, we cannot use this mechanism that caches in the index, is this stuff visible or not. So Postgres can actually cache in the index that nobody can see this row anymore. You don't have to see it. If you want to learn more about this, go check this blog post by Laurens Albe about killed index tuples. This will explain what's going on here. But what this all means, that's that every time we want to find a task that is in to-do state, we have to go through the whole index and find for every index tuple, go and read it from the table and see, is this row visible or not? And then we find, okay, this was updated, I can see it was updated. Okay, we can ignore this, go back to the index, find the next one, and repeat and repeat and repeat. And we have to do this like hundreds of thousands of times. And this is why we are looking at so many different pages there. And none of this work is actually visible in the explain plan. So we see that the pages are being accessed, but we cannot tell why. The actual fix itself is simple. If we have a long-running transactions, just kill it, and to avoid it next time, let's add some timeouts to the system, so queries cannot run for too long, and if somebody leaves a transaction open in the idle state, then there is a backstop and this connection gets terminated and the system can resume going. And in Postgres 17 there is even a fix, so we can do a full limit on a transaction, so no transaction can take more than 5 minutes, for example. After we terminate the naughty connection, everything goes fine pretty quickly. The first query that scans the whole index will figure out, okay, this row is not visible to anybody anymore. We'll set the bit in the index that this is killed. And the second one that comes around can already ignore it and only has to scan the dead index tuples. And a bit later, auto vacuum will come around and just clean everything up and everything will be nice and dandy. So what was missing from our explain? Ideally, we would want to see how many rows were actually scanned but were not visible to us. So right now we are only seeing rows that we actually found that are visible to our query, but we might have been looking at many other rows. It would be nice to see those. Some insight into how this index kill tuples thing works would also be nice. So if we are scanning index tuples and we see that we don't have to follow it, would be great. Or if we did have to follow it and it was killed, again, good information. And yeah, this stuff, we were looking at index scans here, but the same stuff can happen with sequential scans, bitmap scans, all of this stuff. And it just isn't as easily visible as it was in this case. But not done with visibility just quite yet. So let's look at some visibility stuff, visibility map stuff. And for this one, I need a slightly larger table. I'm going to generate a table that has a filler column of 100 bytes, and we add 6 million rows of it. So that would be basically about 600 megs of table. We create an index on the number column here, and we vacuum analyze this table, so we then are able to use index-only scans on it, which requires pages to be set all visible. And now our query that we are going to be looking at is quite simple. We are just going to read one number from this table, and that's going to be using an index-only scan. The index-only scan tells us that it didn't have to look at the table. Everything was decided from the index. But somehow our buffer hit count is about 6 million and a bit. And we take notice of the time also that it takes, that it's about 1 second to run this. So why were we accessing 6 million pages for this stuff? The reason is that the index-only scan, to decide can we give this row out immediately or not, we have to check is this visible to us, and we go and check it from the visibility map and see if the visibility map says yes, we can immediately give it back. And for this we need to find the visibility map page in our cache. So that's a hash table lookup, and we find the page and then we can read the bit from there. But because the hash table lookup still takes some time, this thing caches the last page it was accessing, where it found it. And when it comes back, it says, okay, is this the same page? And is it still in the same place? And if it is, we can just skip all of that buffer lookup and we can immediately access it. Our example here was constructed in this way that this cache never does what it wants to do. So every time we are looking at the next row, it's going to be in a different place in the table, and we have to look up the visibility map page. And right now we did this Trixie table here, but in real world this can happen if you are using UUID based primary keys, for example, and your table is more than 1/4 of a gigabyte large, then this basically will happen. So to fix this type of thing, you just have to keep in mind that data locality matters. So stuff that is accessed together should be stored together. because there are caches everywhere. There are CPU caches and caches in places you haven't heard of yet. So make sure data is stored in the same place. And to do this, we can use maybe a cluster to just resort the table in this numerical order. And if you do this, we can execute the same query twice as fast. And in this case, we didn't need to look up the visibility map page for every time we access the row. And now, as a final chapter, we're gonna go look at index conditions. So we are gonna go back to the tasks table that we had earlier in the visibility map section. And now we have a new goal. We have this query here where we are trying to look at everything in this tasks table from job number 3 that was added before some timestamp. And we want to order this by the ID column to find all of the stuff in correct order. And let's try to figure out which indexes do we need to make this stuff fast. So here are 2 options for the index. We can create a composite index that is sorted by multiple columns, and we can pick the order of the columns that we are using in this index. So as a first step, we are doing an index based on job ID, and then the timestamp. And then the second case, we are doing job ID, timestamp, and then the ID column. And if you look at the resulting explain plans, we see a few differences between those 2. So one of them is that the bottom one is only accessing 3 pages, the top one is accessing 300 pages. But interestingly, the index condition that we are using is exactly the same. It looks like we are using the same condition to find stuff in the index. And the time also is quite a bit faster in the bottom case, even though we have to sort the data. And so what's going on here is that we have to understand the order in which data is stored in the index to see how it is being used. So if we are doing an index range scan, which basically means that we are looking for a range of values. In this case, it was based on the timestamp column, where we are comparing the column with an inequality to a constant value. We can only do this type of range scan if all of the preceding index columns have an equal sign on them. So we have fixed those values in place. So in this case, where we had the job ID was fixed, but everything else was open, except the added column, we had an inequality. When we are storing this in this job ID, and added order, we cannot use this added for scanning the index, because the stuff for job number 3 here will be stored in ID order, and the timestamps will be all over the place. At least the planner cannot rely on them being in order anyway. So we have to scan all of the values for job number 3. But the planner is somewhat smart, so it can use a trick here. We can still evaluate this inequality constraint without looking up the stuff from the table. So in the index, we have the information what the timestamp is, so we can throw out any rows that we don't need. So we are basically doing a sequential scan within an index for everything that has job ID number 3. But the fact that this index condition is only used for filtering is not visible in the explain plan. And what is also not visible is the amount of index tuples that we checked and saw that we didn't need and throw away here. So if we go back and see what was the we didn't even have any information that stuff was removed, rows removed by filter, because that value only includes stuff from the table. So if we discard the value from the index, we don't know about it. And yeah, that's about it about this index conditions. It's really important to understand how their actual ordering is happening. So when we have this multiple conditions case here, can we use the index in a useful manner, or are we using it in a not useful manner? And unfortunately, right now, explain plans are not helping us to figure out is it being used correctly or not. And that's it about explain plans. So what did we learn about here today? So explain really still doesn't explain everything. We can improve explain, and hopefully we'll add some more stuff. And there is plenty of different things that I didn't include in this talk that would be also good to improve. But the stuff that I did include is some of the stuff that I have been seeing in the field the most. And explain is always improving, so once we get some patches into Postgres, maybe we'll have some more visibility into how our plans are planned, executed, and running. And maybe in next year or in a few years, we can do a talk on how Postgres fixes those issues. Okay. Thanks, everybody.
Thank you for all the insights. Are there some questions to this topic?
Hi, thanks for the nice talk. In one of the slides, you said that the transaction to be done is in the repeatable read mode.
Yeah.
I wanted to know why, because in my understanding, it can open the transaction, take the lock in whatever isolation mode there is, and then the other transactions cannot do the vacuum, or actually they update and vacuum cannot proceed. So the specific question is why isolation mode is repeatable read here.
So the reason why I did a repeatable read here is because in the default read committed mode, once the select query executes, the snapshot is released, and it's not actually holding anything back. So because in read committed, every query gets its own snapshot. And once the query is done, the snapshot can be released immediately. But in this case, I wanted it to remain open, so that's why I used repeatable read. So the snapshot that needs to see the old data.
Okay, thanks.
Thank you. Please, any hint how to detect the toasting during sequential scan?
Other than profiling, not really. There is some statistics we use about toast access called PG stat exact that will give you how many toast accesses have we done in this transaction that is running currently. So you can open a transaction, run your query, and check those statistics views to see how many toast accesses we did.
Thank you.
Any other questions? Okay. Thank you, Hans, for your talk.
Thank you.